I'm late. Welcome to EE123 Lecture 13. Woo! Sorry, I haven't noticed. Too busy. Okay, so how are we doing? Friday. Monday is midterm. It's not looking well for you. I'm just messing it. It looks really hard. There's time. Right. There's time for me to make it easier. It'll be hard to make it easier. Okay. So any issues that you had with a pre-lab? No issues? Everybody worked? Yes. That's great. No, because it's like there's always issues. So I'm glad it worked. Okay, that's fantastic. Midterm 1 on Monday. We have a date also for midterm 2. It's April 4th. Okay, April 4th, 4/4. It's a good day to do a midterm. Okay, that's the last one. And after that, you have time to work on your project. Okay, so from April 4th to the end. And so it's going to be substantial projects. Okay, so that's our aim in doing this. Okay. I wanted to go over some interesting stuff. So gravity waves. Recently found evident that there's gravity waves exist. It's quite amazing. If you think about it, like space-time, it's like space-time is like fluctuating around us all the time. It's a small scale. It's a small effect, but it's detectable. And so when two 30-mass sun masses, black holes, go close to each other and start oscillating, they create a huge disturbance in the force. And that can be picked up a few billion years later, something like that, at very, very far distance on a planet Earth, where people have constructed these two sensors that are actually able to have that accuracy, which is insane. It's a feat for science, engineering, whatever you like, humanity. Unbelievable. But if we're talking about DSP, there's a really nice tutorial of how to process these data sets. You can go over there, and it's all in IPython notebooks. Okay, so they have some intro, how to load the data, where to download all this data, recognize all these. Once you load the data, then you can look at it, and here are some plots from signals picked up from these two sensors, the strain measurements, and then you do some spectral analysis of them. Yep. You do some filtering to normalize, and then kind of like look at prediction of what should a signal coming from these massive black holes rotating around each other should look like, and it kind of looks similar to what it should look like. So they actually look for. So what they do in order to look for these events, they try to predict what kind of event can be in the universe. They go and they simulate what they should be, and then they do match filtering with data. So it's one of the things that it's done. But they do some pre-processing. I guess spectrogram. That's our previous topic. If you look at the spectrogram, these are not clean. There is some signal over here, I think. And then if you clean it a little bit, zoom in. It's hard to see here, but there's a chirp. There's a chirp. The universe is chirping. Yeah, the gravity is chirping. So anyway, so take a look at this. It's quite interesting, using classical DSP to do this amazing work. Basically, everything we cover in class shows you here how to process that data. Designing notch filters, low-pass filters, looking at spectrogram, time frequency analysis, things like that. Okay, so worth a shot at looking. Okay, any questions before we move on? I know it's Friday. I know there's a midterm on Monday. But this is overwhelming. Overwhelming. All right, so today my favorite lecture, it's about Lab 2. Okay? Lab 2. And then we're going to continue. I had this vibe last time from the last lecture that, you're looking at me like sheep. Like, huh? Some of you. And so I'm going to go back a little bit, and I made a few more examples on the wavelets, maybe to try, for those that are still a little bit confused. Hopefully that will be resolved. But before this, I want to talk about Lab 2 because this is part of the things that you'll have to do, and I don't have time to talk about on Monday because you'll be working on your midterms. So let's talk about SDRs. So you're getting these SDR, software-defined radios, and this is really the electronics that's in. RF comes in. You got a chip. This one, it uses a Lonix 4000. Most of you don't have that one. You have another chip called, I forget. I forget what the name of that. But from another company called Rafael Micro. And so it's another chip. But what it does, this is a tuner. Basically, it performs low-pass filtering in the IC or bandpass filtering, and it does demodulation. Okay, it does demodulation and brings you down to whatever frequency, it brings you down to an intermediate frequency. This particular one brings it to an intermediate frequency, which is DC. The Rafael Micro bring it into an intermediate frequency, I think about 5 megahertz, but I'm not 100% sure. Something like that. And then after you bring it down, you got this chip over here that performs the A to D conversion, and then samples. It has also a implementation of a USB protocol. Then samples are sent through USB out into your computer, and you have a driver that knows how to talk to these chips. Knows how to tell this one to tune to a particular frequency, knows to tell that one to sample at particular rates, and applies certain filtering and decimation, actually. So there's filtering and decimation happening over here. We'll talk next when we talk about sampling, what does that mean? Filtering, decimation, what's the limitation and implementation of that? But the samples you get out are complex values. Yeah. It's really 8 bits, but but the last bit is not. I think it's 8. It should be 8, but. Yep. Pretty much. 256 values, that's it. But you'll see that because you sample at a high rate, you actually gain more bits. Crazy, right? We'll talk about that when we talk about sampling. And then samples out, okay? So the question is, why the sample is complex? I mean, this is RF in. How can that be complex values coming out? Doesn't make sense, right? The real world is real. It is not complex value. Complex values is an invention of human beings. It's a really nice mathematical way, but a mathematical representation, but it's not real. So what does that mean, even? Aren't you curious? Are you curious? I was curious. It was shocking. How can values be complex? Well, for a person that does MRI, when we always deal with complex data, it comes really natural to me. But if you think about it, it's actually quite simple. So everybody install this, got it working, right? How is this computed? Well, you get data from the SDR and you compute FFT. Okay? And then you compute over a window. Okay? And then you look at the spectrum. Okay? So the middle is really, you compute the spectrum about a certain point, right? Like when you compute an FFT or a DTFT, then you've got the zero frequency and you have the higher frequencies, the Nyquist frequency, and you span basically minus pi to pi. And these frequencies represent minus pi to pi. They also represent, in this particular case, 161 megahertz to 163 megahertz. But it's really minus pi to pi, okay, in discrete frequencies. They have correspondence to the analog ones, but once they're samples, they're minus pi to pi. So you stare at this spectrum. What's obvious from that spectrum that you can tell about the signal in terms of its symmetry? If my samples were real, what should my spectrum look like? Conjugate symmetric. Do you see here any symmetry about the middle? No. So in order to represent that part of the spectrum, I have to have complex values. Right? I have to have complex values. Otherwise, if I compute the DFT or the DTFT, I should have a conjugate symmetric spectrum. Make sense? So it has to be complex. But how do you get complex? And why even it is complex, right? I mean, we know that it should be real. And yes, it should be real. It should be real because if you actually look at the symmetry around 162 and minus 162, yeah, that should be conjugate symmetric. But it shouldn't be really symmetric about this. Okay? So if I crop this part of the spectrum and I bring it down to DC, this is really what's happening here, then that value should be complex. All right, so now that you maybe kind of get it, but kind of not get it, yeah.
The complex value doesn't come from the sensor, it comes after the filter.
It comes from the way we represent the data. The data is real. I mean, this is 162 megahertz. I'm not giving you the whole spectrum. I'm just giving you 2 megahertz of the spectrum. Right?
But the sensor is still sensing real values.
Absolutely.
Okay.
It is sensing real values. Okay. That's right. Yeah. All right. So now let's look at, FM radio. If you look at the spectrum, yeah, around 94.1, you've got, a KPFA, it's a radio station. 93.9, there's another radio station, and so on and so forth. If you look at the spectrum is conjugate symmetric about DC. Okay, that is true. It is conjugate symmetric about DC. But when I get samples around 94 megahertz at a rate of 500 kilohertz, I'm going to really look at that part of the band. I'm going to zoom in and only have data coming out of this part of the band. And when I'm only going to look at this part of the band, in order to represent it, I need to have complex values. And so the question is how does this, this thing implement it? When we talk about sampling, you're going to see it more, but you're going to do the lab before we talk about this. So I thought we might talk about this so you understand what is going on. So how do I do this? So the way it's done, what you do is you demodulate. You take your frequency, you demodulate by a complex exponential, you move it to DC, and then you low-pass filter, you remove the other part, and then you sample it. And you should have complex values. Okay? So the way it's going to work is you demodulate. That brings the spectrum to look like that. You low-pass filter, goes away. And then, obviously, you sample this, and it has to be complex because this is a non-symmetric spectrum. Okay? That's great. Vicky, are you messing with us? I'm talking like as if I was you. Right, let's say I'm sitting here. It's like, okay. What is this? Fine, I can do this in MATLAB, but how do I implement this in IC? Right? How do you physically do this? Yeah, I can do this in MATLAB, but that's already digital. But capacitors, inductors, circuits, are you joking? Well, anybody has an idea? What? Cosine. That's a good start. Cosine is not complex exponential, though. If I did cosine, then I would get, one replica here, and then, there's one here, and then the other one will come over it. And Ooh. You multiply by a sine and a cosine. 12 points. 12 points. It's a European thing. If anybody here from Europe, Eurovision. It's a great demonstration of 3 minutes of cheesy music coming from different countries. Anybody familiar with Eurovision? What? Who doesn't know what the Eurovision is? There's a song contest in Europe that each country has a representative and they sing 3-minute songs, really cheesy ones. And then like countries vote, and then 12 points is the best. And it says 12 points. Well, it's a cultural thing. So I'll try to share my culture with you. Even though I'm not from Europe, Israel was participating in the Eurovision. Okay, so yes, so that was a good idea. So here's how it's implemented. You put RF in, and then you demodulate with a sine and a cosine. Basically, you demodulate with the same frequency, so you have a frequency generator, and then you've got a phase offset of 90 degrees between these two. So you've got some PLL, phase lock loop, generating a frequency, and then you've got a delay of quarter of a cycle that modulate that one and one that modulate that one. Okay. This one is usually delayed, so this is, you will see it's called the quadrature component, and this one is the in-phase component. So you demodulate by these two, and then low-pass filter, and then you do an analog to digital converter. But you need two of them. So in fact, it kind of makes sense because you kind of need double the rate in order to represent. So this, you get double the rate by doing that because you get double the samples. Okay, so this is called the in-phase component. Once you get those values, and you get values here, in order to store them, you just store this as I, like as the real part, and you store this as the imaginary part. So because e to the minus I 2 pi f0t equals to that. So let's look at the top part and see what happens when you do this. When you demodulate, you basically, spectrum is shifted in one way and the other part is shifted the other way, right? Because you have got two delta functions. And now they overlap. And really what you get the symmetric spectrum. You can decompose your spectrum into the even part and odd part. And so this is really what it's doing. Now your spectrum is the even part. Okay. And yeah, it's real. Now you've got real samples coming out, and those represent the real part, the symmetric part, right? And then you demodulate, then you low-pass filter. You get this, and then A to D. Now you do the sine part, and the sine part, this one is flipped, and then modulated, right? Because that's what you do. Sine is I and minus I. Okay. And so now you got the odd part of the spectrum. Okay. And then you digitize that. Low-pass filter and digitize. And so you've got the even part, the odd part, then you can reconstruct the spectrum by combining them. Okay. So this is one way that you could do this. The other way you could do it is not demodulate all the way to 0. You could have demodulate all the way to an intermediate frequency that's close to 0. And then, do real sampling, but at double the rate because you have double the bandwidth. We'll talk about it more. But there's other ways of doing this. When you do this, there's obviously could be some issues. First of all, if the two channels here are have some discrepancy between them, let's say there's a bias in this one, or the gain is different in each one of them, then the cancellation of the negative part and the positive part will not be correct. And then you'll get what's called an image. And I don't know if you heard the terminology image rejection, but when people design IC circuits for RF, there's this thing called image rejection. How good is your ability to get those two together and get the good gain? But here's the diagram of the Alonix chip. Okay, I think they're bought or they went out of business. So that's why there's Raphael Micro. But RF comes in, low noise amplifier. This is the RF comes in. Here you have a PLL that you can control using software that produces a frequency. And then you've got two mixers. One of them is the in phase. One of them is the quadrature components. Then those are, I'm not sure, digital to analog converters here. I think you can control the gain something, or I don't know, I'm not sure what these are for. But then you've got low pass IF filters. And then you've got two gains coming out, two signals coming out. And then the other chip samples those. Okay, the RTL chip samples these. Does this make sense? So it's really how it's implemented. Now the question is like how good is implemented and things like this. So that's the quality of the IC. But that's what's done on your phones. That's what's done on this type of chip, and so on and so forth. Yeah. Yeah, you want it to be the same. But it's two different devices, you know. Like, what if this transistor is a little bit different? I mean, like, there's variations, you know. So there's always variations. I mean, you'll see when you do the radio lab, right? You're gonna, absolutely. I put audio in, you know, I transmit, I receive audio, you know, I get it, right? No, because you're gonna be transmitting next to RF, next to wires that are gonna go back and mess with stuff, and you get interferences, and all of you are going to sit in the same room working together on the lab, putting their radios next to each other and like transmitting 5 watts into your laptops, and like, my lab doesn't work. The USB is going to go out of synchronization because it's just completely saturated by some RF that just, you know, knocked it down. You have to pull it out, put it back in. You're going to deal with all that stuff. You're looking forward, right? But that's real. I mean, it's real issues that come in every system. Okay. So this is that part, the SDR. This is how the SDR kind of works. And we'll talk more about what does that mean, sampling and the rate, and aliasing and filtering and low pass, and like what's the noise that you have, and quantization noise, how many bits really you have, and so on and so forth. We'll get to that. Actually, next week we'll start that. But I want to talk about the lab. So now the lab, the first thing you're going to do is you're going to tune to a frequency around 162 megahertz. And around 162 megahertz, there's the NOAA weather channels. NOAA is the National Oceanic Atmospheric Agency, maybe, or something like that. And what they do is they transmit from various places in the country weather information, and those on around this frequency. So 162.4, and then 425, and then 450, and so on and so forth. They have like 6 channels, and some radios you have the NOAA weather in them, but it's really rare. So people that go to the ocean, you know, marine vessels, you know, they have NOAA weather capability on them. So one transmitter is on Mount Diablo. One of them is in San Francisco, Twin Peaks. And I think this particular one here, 162.4, and that's the range that it covers. Okay. So what you're going to do now is get a certain size of 2 seconds, I think, out of this, and then take 8,000 samples and compute a DFT. And when you compute a DFT of 8,000 samples, you get a certain frequency resolution, right? 1 over that time, and so on and so forth. And you're going to see the spectrum, and the spectrum is going to be a little bit noisy. That's how it's going to look like. And instead of that, what you're going to do then is look at what's called an average power spectrum. So in order to look at the spectrum and kind of remove the noise, sometimes you don't need that amount of resolution. Okay, so a spectral resolution, you can trade off that spectral resolution by reducing noise and averaging across time. If you have a approximately stationary signal, you can do that. And so if you do this, and you only take windows of 800, and then compute the DFT, take the absolute value, and then average those results, the spectrum looks much cleaner. And you see a few stations here. There's 162.4. This is this one. This one. And this is a spectrum I took in the East Bay. So the one from Mount Diablo is much higher. But I have a really nice antenna. I pick up actually quite a few more from Monterey Bay and other places as well. There's another station here, which is CBS or something. They have a station over here, but that station is really to link different stations together for AM transmission. So they do FM over relays, and then they get to the AM station, and then they transmit that. Anyway, I don't want to talk about that too much. Some other stuff that you see here are not real. So this one, actually not real. These are because this is so strong, it's saturated, created nonlinear, and you can see like images of that one. The other thing that you see here is a peak at what's called a DC offset, and that's because this particular chip, if you have a DC offset on your A to D, anything that's DC that you sample, if you compute the Fourier transform, it will give you a peak in the middle. Okay, so that's one limitation of this particular design. You always see a peak here in the middle. So you want to have your station a little bit off. Okay, so you're going to compute this and look at the spectrum, and that's great. Then you're going to tune into a different place, 88.5, which is NPR radio. And you'll see the FM, the average power spectrum on an FM station, which is this one. Okay, this is mostly voice over there. They don't like playing music. They just talk, blah, 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 blah. And so this is the signal that you are going to get out of them. But there's weird thing that shows up on the sides, these flat bands on the sides. And those turns out to be digital radio. So they put digital radio close to the stations. They transmit the same information. But if you have a digital radio will actually demodulate these. If you have an analog one, it demodulate that one. Okay. Unfortunately, in the U.S., which is the land of the free, digital radio is proprietary. So there's no open source way of decoding that. It's all licensed. Somebody pitched that to, I guess, Congress or something, and they decided to go with a closed format. As opposed to Europe, which is completely open. If you want to use this device to listen to radio in Europe, no problem. Okay. So. Home the brave. Okay, but unfortunately, we cannot decode that. It would have been great, but we can't. Yes.
You say 88.3, but it's 88.5.
It's I guess the center is 88.2. I'm sorry.
Oh, I mean, like, but the peak is on the right.
This is 88.5. Yeah.
So what?
So the spectrum around 88.3, and I think I actually demodulate at 88.2, or I don't know, where's 3? Here?
So is that because we want to shift it? Like,
Yeah, I wanted to shift it to the right. I just wanted to look at the spectrum. It's not like you just go there and you see what happens, and then this is what you see.
So if you put it in the middle, then you get that real.
If I put it in the middle, then this would have shifted here.
And that's totally fine also.
Yeah, that's fine.
Okay, so you don't get that real peak that you were talking about.
Right. Yeah, the real peak is still here, right? But it's small compared to that signal. Okay, that's another thing that you're going to do. And you're going to look at the spectrum, and it's not so interesting in the sense that you're not going to see its dynamic. The next lab, you're going to do spectrograms and demodulate that and all that stuff. Okay, but that's lab 3. Then what you're going to do is we're going to look at ADS-B signals. So ADS-B is secondary radar. It's called mode S. And there's a primary radar is a radar station that is the usual radar. It kind of rotates, sends pulses, and receives signals from airplane. And that's for airplane traffic control. There's another mode, which is called mode S, ADS-B, in which each airplane has a transmitter, and it's called a secondary radar, where they are actually sending their own position based on GPS. Okay, so they call it radar, but it's not radar in that sense that you interrogate it. well, I guess you interrogate it, and then they'll send a packet with their information. Okay? And it gets picked up by satellites, it gets picked up by other planes, so everybody knows where everybody's going. The thing is, it's all open, it's not encrypted, so everybody could listen to it. Fortunately, also fake it. So if you have a software-defined radio and you're a malicious bastard, then you could, fake it and create fake airplanes. This is not even amateur frequencies. You can do software. Like everybody can buy a software radio and do this, which is a problem in terms of safety and security. But it's a secondary system. It's not the primary system. It's not. I think people have maybe thought about it, but didn't think about it so carefully when they designed that system originally. And so now there are considerations maybe encrypting it or putting some certificates on it and all sorts of stuff like that. But the frequency is 1090 megahertz, and the rate that the packets are sent are at 1 megahertz. So 1 megabits per second. If you sample it 2 megabits per second. If you sample it 2 megahertz, you're kind of in the Nyquist and be able to resolve this in some way. There is some aliasing going on, but because these are square wave, like the packets you'll see are not impulses, but or not just pure frequencies, but you can still resolve it with this very cheap system. $15. Okay, so when airplanes send these packets, they have what's called the preamble, which is about 8 microseconds, which looks like this. And it has a particular timing so that you know that the packet starts. And what you're going to do in the lab is look for these preambles. That's the idea. You want to look for these preambles and then crop a packet, decode that packet, and then once you have those bits, Frank wrote a decoder that interprets what the bits are and then gets information like what is the plane, where it's heading, and where its location. Okay. So there's two different type of packets. One of them is there's a short squirt, and then there's a long squirt. The short one is 56 bits. The long one is 112 bits. And it is encoded with what's called Manchester encoding. So an on-off keying. So here's how this is amplitude modulation. Okay, packets are amplitude modulated. And normally with amplitude or on-off keying, a bit of 1 is when there is something, a bit of 0 is where there isn't. In Manchester coding, you do something else. You encode a bit through transitions. Within a certain time, which we call a chip or a bit length, if you have a transition between high to low, signal to no signal, that encodes a 1. And if you have a transition that goes from no signal to a signal, that is bit 0. Okay? So the information is encoded in transitions as opposed to being high or low. The nice thing about this is always transition within every bit. And so you can get the clock rate automatically from that. Okay, you can figure out how fast things are going. And so this is a very useful way of encoding things, called Manchester coding. And so this is taken from, I think, Wikipedia. Ideal. This is what we measure with the RTL SDR. And you can kind of see the preamble. There's noise and there's interference, and it's not ideal, but you can obviously see the preamble. And then here you can see the bits. Low to high, high to low, low to high, high to low, high to low, high to low, low to high, high to low. Cool, huh? And so what you're going to do next is acquire data. You acquire 1 second. And this is like fishing again. If there's airplanes, you'll be picking something. If there's no airplanes, you'll basically see noise. Okay, so pay attention also what the intensity is. So the intensity should go, I think, from 0 to 1 or 1.4 or something like this. That's what the intensity should go to. But so if you see really low values and very quantized information, then it means that there's probably no packets there. And the graph only was scaling everything up. So what you need to do is to acquire data till you get some packets. And there's airplanes all the time. So Oakland Airport, there's SFO, there's always airplanes. So there's lots of activity. But if you do this lab at 3 a.m., maybe there's not going to be an airplane for like 5 minutes. Okay? So you have to repeat till you get an airplane. We also recorded data for you, so you can use that if you don't get airplanes. Okay, and that's on the website. Okay. One thing that's really important, if you're at the basement of Corey doing this work, obviously it's not going to work well. 1 gigahertz doesn't penetrate through buildings. So it's important that you be close to a window, wooden house, it's okay. Go outside if you need to. You'll get better reception. These are also not great antennas for 1 gigahertz. They're okay, but not great. Okay, so just know that. So after you do this, you're going to extract one packet, figure out where it is, and then look at those packets and then decode like a few bits of them manually. Then you're going to write a function, two functions, to find the preamble. One of them uses normalized cross-correlation. Okay, so you know what the signal you're going to look at. You're going to do an autocorrelation, cross-correlation, but it's normalized. So it's going to be always normalized between -1 to 1. And so if you have high correlation, that means that you have a chance for detection. Okay, you're going to do that, and then extract packets, save them in a matrix, and then display those energies as images. And you see that they're aligned nicely. So each row here is a packet. And you see the packets kind of align nicely, and you see 2 long squirts and many, many short squirts. Okay? And you can see the preamble. The next thing you're going to do is use another nonlinear feature detector that is based on logic, based on the fact that if you have this type of a packet, things should be bigger than each other or smaller than each other versus distance, as opposed to doing autocorrelation. As it turns out, this turns out to be more robust than this normalized autocorrelation. And so this is what you're going to do. One thing I didn't mention is that before searching on everything, you're going to threshold it based on the noise level, and you're going to estimate the noise level using what's called a maximum absolute deviation, which is a way to estimate the variance that is insensitive to outliers. Because when you see these packets, if you just computed a standard deviation, then it would be really heavily weighted by those large signals. And so you're going to use an estimator that is insensitive, and guess what it's based on? Like the median, right? The median is insensitive to outliers. Okay, so you're going to compute that. And so you're going to crop the packets based on some, factor of the standard deviation, then get those, and then try to look for the preamble. When you do that, you get maybe more packets using the logic. Once you decode bits, you're going to go to the real-time part. You're going to use your functions into Frank's decoding code. And then that will show you airplanes in real time on a Google map. So this is an example of American Airlines 1522 that was flying, over the East Bay. Any questions? And this is what's going on right now. Oh, wow. So this is live running right now. No, no. This is this one. Like you're getting it right now.
That antenna isn't strong enough to get anything over like San Francisco or anything like that.
It is if I was outside. This is blocked. I mean, I'm getting really stuff that's above us. Pretty much. So it found a packet over here, but now it's still looking for packets. It doesn't see any packets. Right? So there's no airplanes right now going above us. But once it detects, then you'll see. So look at this, like when you run IPython Notebook, look at the terminal and see if it's actually working. You know, we did the best of debugging this bouquet now by downgrading it and so doing all sorts of stuff like that. So it worked, but you know what? It worked on n equal 4. So we're quite confident it should work. So we're just going to blame you if it doesn't work for your implementation of the preamble. Okay, pretty much. That's what we're going to blame if it doesn't work. So no packets right now, of course, because I'm doing a demo. But you saw how many planes we picked, right? Unknown, American Airlines, whatever, something like this. And it's pretty cool. You're going to see them moving, you know, on the map, and it updates really nicely. Yeah. Questions? Yeah, absolutely. I do that all the time. The problem is with on the flight, you don't have like internet, so Google Maps don't work. But you can get the coordinates and put them on Google Earth. And you see, I do that all the time.
So we could make an offline version of it.
Yeah, you could. Yep, absolutely.
How often do airplanes send these?
I think 2 a second. Okay, so it's pretty. I mean, I think it's pretty nice. It would be a nice experience to go through, and of course, there's no. One thing you can do to validate that there's actually airplanes is you're going to find this shocking. You go to this website, which is Flight Radar. Have you seen that one? They actually use a lot of ADS-B data that people send them. And yeah, there's lots of airplanes going on right now. VRD 11. And this one. Let's see if I pick him up. Of course I don't. Let me just restart this. See if that worked. Okay. And then we're going to run it again. Oh, one thing that happens here, this is a bug again, that if it's an empty, you just resize the window. Oh, there you go. Shows up. Okay. Yeah, nothing. Okay. Inside the room, it's really hard to get something. All right, let's move on. If you go to Flight Radar, by the way, you'll be shocked how many flights are in the world. Ridiculous, right? Yeah. It's quite amazing. Okay. So the one thing that we talked about last time was what happens when you have orthogonal Haar, and how is this mapping between, where does these occur in space and frequency, in time and frequency, the frequency tiling of those Haar. And if you notice, this is the fine scale Haar wavelet. So they're localized. If you project your signal onto this basis function, you're really looking at differences located at this part of the signal, here at this part, this one, and this, and so on and so forth. And it's high frequency changes because it's localized difference. This is less localized difference. It's one that side, and so on and so forth. But one thing I could do is plot the spectrum, which you can actually then see what is the localization both in time and space. So if I look at the fine scale ones, if I compute the DTFT of those signals, it's going to look like that. Okay, that's the magnitude spectrum of those signals or those basis functions. So they're localized in high frequency. They cover almost half half of the high frequencies, right? If you look at full width at max, full width max, half max, full width half max, right? It covers half of the spectrum. Okay, they're localized in space, only cover 2 samples, and they cover the half of the frequency. What's the difference between the DTFT of these two? I mean, they all have the same exact magnitude, but they have different phase. That depends where they are, right? But the same magnitude, right? Because they're just shifted versions of each other. So that's where they are, both in time and frequency, right? They cover half the space, half the frequency spectrum, and they are localized by 2 samples, each one of them. Okay, in time. Does this make sense? Now a little bit more visual. Now it's not, it's not like completely isolated, but they're localized in that area, right? They still have low frequency components, but that's not what the support is. So it's more of an illustration of where they are, right? They still have energy here, but really they're localized here. Okay, what's about the next scale? The next scale, if I look at the DTFT, it looks like that. So it localized in this part of the spectrum. It's a little bit more narrow. Narrow spectrum, wider support in time, which correspond then to these places in the frequency tiling. And then the last part of decomposition is, this one, which corresponds to this blue. Again, more localized and shifted to the left, corresponding to the green part of the spectrum. So 8 length in time and a small piece of the spectrum. And then I have to plug it with a low pass. The low pass is all ones, which represent the dotted filter. Again, its width is, by the way, it has another side, right? So its width is similar, and it really represents this part and has a length of time covering 8. Does this make sense? Now, I could not do that, not do this part of decomposition, and stop at level 1. If I stop the decomposition at level 1, I don't go all the way. In that case, I only have the low-pass filters left. And so then I got a decomposition, which now you have a farther wavelet here and another one here, which are located at those places. And they're a little bit wider, of course. Wider because they're thicker in frequency, but not more narrow in time. Okay? So yes, frequency tiling. That's effectively how it's done. That corresponds then to the detail coefficient and the approximation coefficients, and these would be the decompositions of these. And the thing is, you can implement it using filtering. And the way that I described it is that you filter with a high pass and a low pass. You get the approximation and detail coefficients. You then downsample because you have too many. So you downsample them. So now you've got 4 coefficients at that scale out of 8. And then in order to get the second level, then you take the approximation, you filter it again, high pass, low pass, and then now you get, and I fixed the slide, now you get, you break these into 2 and 2, and you've got approximation and details. And then you can go on and break this into approximation and detail again. And that's it. That's done, right? Because it's 8 long signals. The complexity is very interesting of wavelets then. Because if you do things like this, then you've got complexity of n, and then n over 2, and then n over 4, and then n over 8, and effectively it's O of n. So wavelet transform is an order of n. It's not n log n like FFT. It's order of n, much faster. Very efficient transformation. Okay, implementation. As long as the filters are small. If the filters are big, you have to do these convolutions using DFT, which is then n log. It becomes n log n. It depends on the implementation. If filters are small, then it's n log, it's 2n. How you reconstruct, it's also very interesting. And when we talk about filter bank, you're going to see it. I'm just going to show you now. What you do is you take those coefficients, and then you flip the arrows, If you have downsampling, you do upsampling. If you have an error that went that way, you flip it the other way. You replace all the H's with G's, which are flipped versions of the H's. And then you just stream everything that way. Okay? You get the approximation coefficient detailed, you upsample them, go through those filters and add. Now you got then another approximation. Then you take this detailed upsample, take this one upsample, go to the filtering and add. And then you get back your signal. I'm not going to show you now why is this, but when we talk about upsampling, downsampling, filter bank, you're going to see it more closely. Okay? So this is a review. The application, I went over this last time, of how you do this decomposition, and you get this really nice view of the space of time frequency through these ridges, so kind of zoomed out version of your signal. So detailed as you zoom in and then zoom out. But what's really interesting is how it makes signals sparse. And sparsity can be used either to denoise, like this case, or it can be used for compression, if you just store the largest coefficients. And as it turns out, JPEG 2000 and all the video compression recently, like Skype and things like this, they all use wavelets. Okay, and then for compression. All right. So study well for the midterm. There's another session today, I think. And we'll see you on Monday. Yeah. Thank you. Oh, there you go. Here's a packet. Here's a packet. Oh, there's another one.